So 3.2, measure of variation. This one is a relatively abstract concept. What do you mean by variation, right? Or variance? Everybody, my pronunciation here, I heard some complain about that, right? Even my kids always complain about my pronunciation for this. Okay, I'm trying my best. Variance, okay? That is to use to describe measure data variation. What does that mean? Using human being language, right? So like we have a data sequence here, everybody. How many numbers? 6 numbers, right? What's our goal here, right? We are trying to understand for this data sequence here, they have 6 numbers. How big those data, they have to change, right? So we want to measure that, right? So how do we measure, that's what we call variance, variation. So there are step-by-step calculation for this variance calculation here. Everybody, first one, we are trying to calculate out of the 6 data points, what is the average? Everybody, you see that X bar here, okay? Sometimes you see, like I have kind of a small x or bigger x, right? But the bar is always there, right? So how do we get the average? We add all those numbers together divided by total number of points. So we got 35. And then we write down 35, 35, 35 here, right? Question, why do I write down that way? So this case here, we are trying to get the difference of each one, right? So you can see that I put, let me see, like this one here, x1, right? X, like you can see this, I put the xi as a notation. So you can see this is like x1, x2, x3, x4, and so on, okay? And then this is the average. Now, what's next is we are trying to calculate the distance of each, everybody. So it's like x1 minus x bar, 35 minus 35, because the average is 35, right? Got 0. 45 minus 35, 10, 35 minus 30 minus 35, negative 5, and so on. So that's the data sequence we are getting here, right? This is the difference, right? That's a difference data sequence. You see that here. Now, what's happening? Yeah, go ahead.
When you find the distance, I see that you're subtracting,
Yeah.
but what numbers are you supposed to select? Is it random or something particular?
Which number we are going to select? I didn't get that. Which number? All the number here, this data sequence is given, right? This average, we got it from the calculation. So no number here is random.
He's subtracting the sequence from the mean that's calculated.
Yeah, yeah. Like we got this one from, so that's the reason I put this one as like a table way. Is that right? Like a row, column by column, like that. Yeah. Does that answer your questions?
I guess. I would have to also see it on a paper to see how it's laid out so I can better understand it.
Okay. Okay. So that's the data sequence. Do you know how to get this data sequence?
I presume using the formula, the xi minus the average.
That's right. Yeah. Yeah. And what's next step here is, intuitively, if we are trying to say the average change, because this is the mean, right? That's the average. So each data points, we can see the difference from that average. Sometimes 0, like perfectly on the average. Sometimes positive 10, sometimes negative 5, right? So ideally, if we are trying to measure the average distance, like intuitively, we will say we should add them together divided by 6. That would be the average distance. But the trouble here is, if you do add them together, what's happening? 5, negative 5, 10, negative 10. Then you say, add them together, divided by 6. You got a 0. You say, the average change is 0. There's no change? Not really, right? So that's the case. We usually have, if we do this directly, all right? Xi minus X bar, that's not enough. We have to go further. We have to go further here. We want to get rid of the negative impact. So how do we get rid of the negative impact here? One of the common way is to take the square. Everybody, take the square of each one. 0 square, well, still 0. 10 square, 100, right? Negative 5 square, everybody, got 25, right? Negative 10 square, you got 100. So you see that now you have a square all of them, and then you don't have to worry about those negative numbers, right? Now you add those numbers together, everybody. You add those numbers together and then divide by, tricky part, everybody. Intuitively, we would say divided by 6 because we have 6 numbers, right? So in statistics, we are using the way that dividing by n minus 1. So what's happening here is in statistics, people doing a lot of research to find out using the division by n minus 1 is going to be more stable, more accurate than using the n divided by n. So in other words, from now on, we are going to use everything in the formula. Whenever we talk about variance, everybody, whenever we talk about variance, we are talking about this formula. I don't want you to get confused, okay? And that is the most common one, okay?
Professor?
Yeah.
So if that's a formula to find variance, then the one above it, well, what's the formula dedicated to find?
What's the formula dedicated to find? So
There's a one right above the red box, where it says xi minus x average to the power of 2.
Yeah. That's the one. You see that in the formula here. You see in that formula, we have this, each pieces here. Let me try to highlight. You see that piece here? Right? That's what we have for this piece here. So in other words, like each one, you have a square, is that right? Square, right? So xi minus x bar square. So the first one is x1 minus x bar square, x2 minus x bar square, right? Did you see the previous one here? That's xi minus x bar. Follow me?
Yeah, I see what the pattern. I was just wondering what it was for.
What is for is to help us calculate the variance.
Oh, you're just showing it step by step?
That's right. I mean, exactly using this step by step so you don't get confused. I mean, all of a sudden you jump to here. Why? How? Okay. So that's the one I'm doing step by step here. I hope you got that. Okay.
Okay.
Now, so we got the answer here, 50. Everybody, that's what we call variance. Remember, when we calculate this variance, we did a square, right? So that's not really when we set a distance, is that right? Or change, right? So in other words, we kind of want to get rid of the square, right? When we say the average change, right? So how do we get rid of the square? What we do here is take the square root of that. So everybody, we take the square root here. So square root of 50 to give us what we call this, another concept, one of the popular statistics concept, standard deviation. Everybody, in short, SD, not for San Diego, okay? Standard deviation, one of the most common statistics term, standard deviation. It's defined as they take the square root of the variance. So you take the square root of 50, you got 7.1. So that's what we call, if you really want to measure the average change, that will be this number here. Now, so that's the concept. How do we calculate variance? How do we calculate the standard deviation? I hope it's clear. We have, let me see, in terms of notation, we have some notation I want to point out here. So variance, we can say, write down the variance, right? Another way here we can say is using the notation as square, right? You wonder, where's this S coming from, everybody? The S is coming from the ones that we mentioned earlier when we say SD, right? Standard deviation, everybody? Standard deviation, right? So in this case here, we are using SD for that. That's okay. And even sometimes we are more lazy, okay? So, you will see that in mathematics, in statistics, right? People got lazy. They developed some notation as a lazy way to write down, right? S for standard deviation, right? Because S is the what? Is the square root of the variance. So in that case, you square of that, you got a back of the variance. That's the reason you see that here, S square is the variance. And S itself, what do we call? Standard deviation. I hope it's clear, everybody. So that's the concept of how do we calculate if you are given a sequence, right? So you will see that on homework, right? On the exams, right? Given a data sequence, right? Can you calculate what is the variance? What is the standard deviation? Okay, so hope it's clear. Now let's continue. There's another formula, everybody. There's another formula. I would like to introduce that here, which is this piece here, that formula. This formula here is not that intuitively understandable. It's not, okay? Like you compare with our previous one here. We can do that step by step. First step, what do we do, right? Second step, what do we do, right? So that's what we calculate that. Okay, so we this step by step, intuitively understandable, right? You don't make mistakes. Relatively easy, relatively less chance to make mistakes. Let me put it that way, right? Now, if you prefer the other way, everybody, if you prefer the other way, this is the other formula to do the calculation. So instead of using a step by step here, right, you do this way here. So you plug all the numbers and then you just, add all the numbers as specified in the formula and then do the calculation, you got an answer. But in terms of why, in terms of how, you probably not. So it's totally up to you, everybody. Do you want to use this one or do you want to use the other one? Okay. All right, that's what we have here. Now, we mentioned previously, right, for this group data here, like this example here, right? We know there's a way we can calculate what's the average. We can do that, right? Like similar to that GPA calculation example, we can calculate the weighted average, right? Similarly, we can also calculate what's the variance, what's the standard deviation for this group data. But you will see the calculation here is going to be way more complex, everybody, more complex that here we don't require this, everybody. We don't require this, okay? We don't require to use this this example here. So you will not see any homework question asking you to calculate the standard deviation, the variance for this group data. All right, so that's for this case here. Some notation I want to introduce. This one we will see this several times, right? So in terms of notation, you will see that, let me see if I can write down using trying to find out the mouse. How do I write down? Is this one? Let me see. So you will see two popular concepts. We talk about here. We talk about one is the sample. We mentioned last class, right? Let me mention this one more time here. Sample, that's like a subset, right? A subset of the data, right? Population, that's all we are trying to study, the population, right? So now, when we say the average for those two items, we are using different notation for that, okay? So for the sample, if we say the average, okay? If we say the average for the sample, which notation we are using, okay? We are using the X bar. We are using the X, right? X bar, that bar, right? Sometimes I write down like small x here like that, like small bar here, right? Or sometimes I don't write down that, that's okay. But this bar, we always have that, right? And sometimes they want to say, oh, this average is out of how many data points? You can say like n data points. You can put an n here. Follow me? But for the population, that's all the subjects we are trying to study. We are using a notation, everybody, mu for that, mu. So in statistics, there's a certain notation, certain letter we reserved. They have a special meaning for that, okay? So that's for the average. That's the other thing is for the variance, we call like S square, right? So variance or standard deviation, right? Let me see. It's difficult for me to write down this here. Let me see. I'm trying to see any other easy way. So the sample variance, we have a notation like S. You see that previously, right? S square. That's the sample. What do we say? Sample variance, right? Now for the population, we have a special notation. Everybody, like sigma square. Sigma square. Sigma. If you check the textbook, they have something similar to this. May not be exactly. Usually, I write down this way. All right, they have a little. I think in the textbook, this piece here is relatively short, right? I try to put it a little bit longer so it's more clear. Sigma square. So both of them, they are talking about the variance, right? But you know they are pointing for different concept, right? Whenever you see S square, right? That means what? That's the variance. You see that notation here, right? The variance for what? The variance for sample, right? Whenever you see mu, they're talking about the population average, right? It's not a sample average. Sample average notation, we should use X bar, right? Sigma square, whenever we see that, that is for population variance. Follow me? This is our first time to talk about that. Next time we will I think we will at least mention this twice, okay? This concept here. We will come back here at least twice, okay? Questions?
Professor?
Yeah.
That squiggly cursive D, what is that called?
Sigma?
Really? Is it?
It's called sigma.
Oh, wow.
Talking about this one, right?
Yeah.
Yeah.
Thank you. Appreciate it. Thank you.
All right, let me continue here. So the second concept. Okay, someone was saying using the gig ladder. But mu, let me see, mu, I think you can find out the corresponding gig ladder, right? Alphabetically, there's also a mu here, right? Anyway, the same as mu, yeah. Now, second part here, we want to talk about this coefficient of variation. This is a very useful concept, everybody. Sometimes we want to compare, like you have a two data sequence, right? And you want to see like which data sequence they have a bigger change. The key part here is those two data sequence here, they are talking about like a different stuff. So in other words, they are totally on different scale, right? We cannot simply count down, for example, like previously we calculate the variance and we say the standard deviation is like 7.1. That's the average change, right? The calculation wise, yes, for this data sequence, we got this one. For different data sequence, right, we got a different sample standard deviation, right? How do we compare them? So this concept here, coefficient of variation, is to help us compare different data sequence, which one they have a bigger change. So I want to point out using this example here, everybody. This example here, we are trying to study like the for some car dealers, right? Like every 3 months time frame, right? The average number of car sales in the 3 months time frame, right? Like these 3 months you sold, for example, 89 cars. Next 3 months you got like 85 cars, and then another 3 months how many cars, right? So it's every 3 months you got the number of car sales, and then you take the average of that. You got to say average. They are given 87 cars. And for that data sequence, we can calculate it by ourselves, but this case here is given, right? Standard deviation equal to 5. That's easy, right? Another data sequence here, everybody, they are given for the car dealers, right? So the commission for like each car here every 3 months, right? It's $5,225, like that, right? Every 3 months, right? And then standard deviation is $773. Everybody? I mean, intuitively, those two data sequences, they are related, right? They are talking about the car sales, right? The first one is talking about number of car sales, right? The second one is talking about now for those car sales, the corresponding commission those car dealer they are making, right? So this one is in terms of dollar, right? It's different from the one that like we mentioned earlier, right? This is in like $5,000. This one is like 87. Count. They are not in the same scale, right? We cannot really compare 5 to this 773 because they are not really on the same scale, right? That's unfair to compare that way. So using this concept here, what do we call this? Coefficient of variation. That is to help us compare them like more apple to apple. So in the beginning, you got the orange and a banana like that, right? So you convert everything to apple to compare like that. So the formula is given by everybody. So the formula is given by CVA, right? So stands for coefficient of variation. Is determined by standard deviation S. So if you are talking about sample, right? Remember sample, we are using S. And sometimes we have like small n here to indicate, oh, it's out of how many samples, right? For population, that's sigma. That's sigma, right? And those both divided by average. Is it sample average or population average, right? So in this case here, for the number of car sales, we can calculate the coefficient of variation is the standard deviation 5 divided by 87 multiplied by 100. The purpose of multiply by 100 here is to help us get everything in terms of percentage. Okay, I mean, essentially, when you multiply 100%, everybody, it's like multiply by 1, is right? There's no change. But the purpose of doing that is get a percentage, everything. Okay, so we got 5.7%. Similarly, for the corresponding commission data sequence, right, we can calculate for the CVA, right, coefficient of variation, 773 divided by 5,225, we got 14.8. Everybody, which number is bigger? Which data sequence has more change? Is that clear? Because 5.7 is less than 14.8, then what do we say? We say for this commission data sequence, right? Like every 3 months time frame, the corresponding commission, right? That data sequence is more volatile. So in other words, there are more change potentially, right? What does that mean? If you think about that intuitively, everybody, right? If you go to those dealers, right? I would say, I mean, for the commission they are trying to make, if we did some research, we know how much value for this car, right? It's probably difficult for them to make too much from us, is that right? They make decent, right? But sometimes say we don't do research, right? We just go there, listening to what they are trying to, promote, right? And in that case, if we don't know the reference value for that, right? And they may make more money from us in that case. So in other words, you can see that commission data sequence, potentially, sometimes higher, sometimes lower, more volatile. So that's it. Intuitively, it is making sense. So that's my point here. Okay. Let's see. That's for this case here. Number 3, the third section here, we are going to learn something that is abstract. And I'm trying. Yeah. Go ahead.
Sorry to interrupt, but I just have a question. So like, let's say back to the last problem, we would pick, like, the answer would be 14.8, right? But why we're picking that because like the commission could make us end up paying more or less, or just more? So
the your question here is like, what's this example here trying to do, right? So you have 2 data sequence. Mm-hmm. You have 2 data sequence here. One data sequence is in terms of number of car sales. Mm-hmm. So like these 3 months, you got 80 number of cars got sold, right? Next 3 months, you got 85, for example. And then another 3 months, you got 81, for example, right? That car data sequence, potentially you will see the change. Is that right? Mm-hmm. Another data sequence is for those car sales, right? The corresponding commission they are making. So in other words, those 2 data sequences, they are related because they are both talking about the number of car sales. Is that right? The difference here is they focus on different part, right? The first one data sequence is talking about number of car sales. The second one is the corresponding commission they are making. So how do we compare those 2 data sequences? You can see that they are not in the same scale. 87 and 5,225. Yeah. Right? So we cannot simply compare, for example, previously we say the standard deviation is try to measure how big the data sequence is changing. Is that right? So by itself, we can measure, like we know the average is about 87, and on average, the change is like 5. So it's like a plus or minus 5. You can understand that way, right? But if we are asking ourselves, those 2 data sequence, which one they are more volatile? So in other words, which data sequence they are more change? Okay. That's our goal here. Is that clear? So at the end, because we got 14.8, that's bigger than this 5.7, we say, oh yeah, 14.8 is bigger. So that data sequence potentially has more change. So it's more vulnerable.
Okay, thank you.
No problem. Now, for the third part, Chebyshev theorem. What that mean? It's a very abstract theorem in statistics. You probably don't care about this person here, Chebyshev, right? But I do care though. What's happening here is this person, if you see that, I don't know if I told you, right? I got my PhD in mathematics, is that right? So I have for my PhD, I have my advisor, is that right? PhD advisor, right? And my PhD advisor, right? Here we are got different advisor, is that right? So in that case, if we are, advisor going backward, it's like your father's father going backward, is that right? So you find out what is really my father's father's father. I don't know how many generations away, going backward, okay? So it turns out to be Chebyshev is my PhD advisor. Let me see how many times I need to say. I need to say 9 times. 9 times. So I'm going backward 9 times. That's him. Okay. So that's questions?
Yes, sir. So summary, I actually understand what you said. So the summary is you're not going forward, but you're going backwards, like father, grandfather, great-grandfather. You have to go backwards only?
He's just telling you a story. He's not telling you about math.
Yeah,
Oh.
this one is not about the mathematics. This part, if you got confused, is totally okay. Okay.
His PhD advisor, his
Yeah.
advisor's advisor's
Oh.
Yeah.
advisor.
Thank
Yeah.
you.
So finally, one of the person is him. Okay. So that's the reason I care for him, right? Now, I mean, you probably don't care, right? All right. Thank you for explaining that for me. Otherwise, somehow I cannot explain that easy. Now, this theorem, right? I mean, whenever you see like theorem, I mean, that's a kind of a headache, right? So how do we explain this, right? Using human being language, right? What that theorem tells us, right? So here's a picture. I think this picture will tells you a lot of stuff here in terms of this Chebyshev theorem. If we plug the data, everybody, if we plug the data, like on the XY plane, for example, right? So like I can plug the data like that, for example, right? And then I have like that, right? Like that way, okay? So I have those data points, for example. Now, what's our question here is, after we plug those data points, right? The first common item, or we say the first common statistics we usually track is what? Is average, right? I mean, that's the one we just learned. How do we calculate average? We add them all together, divided by number of data points, right? So in that case, say that's somewhere in the middle, right? Like that line here, right? That's our average, okay? Just for example, okay? Now, Chebyshev theorem is to tell you in terms of the distribution of those data points here, right? Everybody, intuitively, all the data points, they should be distributed around this average. Is that right? I mean, that makes sense. I mean, because meaning is what? Average. Average should be somewhere in the middle, right? You have some points above, some points below, right? So the Chebyshev theorem is to tell you not only that, not only those data points, they should be distributed around this average, but also in terms of like very large portion, they should be within certain distance from the average. So everybody, say we are given all those data points here, right, on the XY plane. We just learned the calculation for the variance, the standard deviation. Remember the standard deviation, right? We just learned the formula for that, right? There are 2 ways to do that. The first one, using the step-by-step calculation, right? Like a table, like first you calculate average, right? And then each one minus average and then square like that, right? So that's the standard deviation. Now, if you have, say, now you got this standard deviation, right? Chebyshev theorem to tell you that, right? If you starting from the average, right? Starting from the average, you go above by 2 standard deviation, right? For example, we find out the standard deviation here is like 5, right? So the average here, for example, is 50. So we go above like 2 of the 5, right? So it's 5 here, so 55, another 5, 60. So this number here on the top is like, for example, right? I can write down this one here is like 60. Average, I mean, just use some example here, okay? Like 50, okay? 50, right? So 2 standard deviation above, what's the number? 60, right? Each standard deviation here, say we are given, this one is equal to 5, okay? And then we can also calculate what's the 2 standard deviation below, everybody? That should be 40, is that right? Now, Chebyshev theorem tells you that within 2 standard deviation, away, right? Within 2 standard deviation away. That means you go 2 standard deviation above, 2 standard deviation below, right? There should be at least 75% of data points fall in that range. I mean, you can imagine 75%, that's like a 3/4, is that right? I mean, that's quite some. So in other words, like there are quite some data points within that range. And it applies for all any data sequence. That's the amazing part that this Chebyshev theorem, right? This Chebyshev theorem here apply for any data sequence. Okay. Now my question here is, I mean, why is that always 75%? No. Okay. 75% here is just example. Okay. So if it's a 2 standard deviation away, it's 75%, right? So how do we get that 75? Everybody, in the formula, you see that here, 1 minus 1 over k squared. What does that mean? So if k is equal to 2, right? So if k is equal to 2, let me write down this, maybe write down this more close. So you know k equal to 2, right? If k is equal to 2, okay? That means like 2 standard deviation above, 2 standard deviation below. Then we plug into the formula 1 minus 1 over 2 square. Everybody? So which is 1 minus 1 over 4. So that's a 3/4. Follow me? Right? 3/4. 3/4 is what? It's 75%. Okay? So that's the for the case k equal to 2, right? 2 standard deviation away. Now, how about the k equal to 3, everybody? Similarly, we can do the calculation.
Would that be 2/3?
That's not exactly the case. Okay, so we have to plug into the formula, right? So 1 minus 3 square, is that right? Because the formula here is what? 1 minus 1 over k square, right? So it's going to be 1 minus 1 over 9, everybody? So if you plug into your calculator, you will get 88.9%. Yeah. So 88.9%. I mean, 8 over 9, right? Yes. So in terms of percentage, I mean, intuitively, it is making sense. Why? Because you check this graph here, right? If you are saying 2 standard deviation away, 75%. Everybody, it's like 75% plus, right? Minimum. Minimum is 75%. Could be more than that, right? But the minimum is 75%, right? Now, if you are saying, how about like 3 standard deviation away, that means I have to cover 1 more above, like that one, like this one here, right? And 1 more below, like this one here, right? So in this new range, will be at least 88.9%. That's bigger than 75%, which is right. Is it right? So, I mean, sometimes from this graph here, it's like almost 100%, right? Could it be more than that? That's okay. But the minimum is what? 88.9%. That's the beauty for this Chebyshev theorem, right? Applies to any data sequence, right? You can have k equal to 2, everybody. K equal to 3, okay? And I want to remind you there's one more case I may ask you is k equal to 2.5. Okay, you can do that similarly, okay? You can plug into that formula to do the calculation. Okay, I'm not going to ask you like too many k choice. K equal to 4, k equal to 5. No, that's not really useful, okay? So I list all the possible choice, k equal to 2, k equal to 3, k equal to 2.5. Okay, now someone would say, how about k equal to 1, right? Even though we have a requirement here, k should be bigger than 1. But if you try to say k equal to 1, what's happening here is 1 minus 1. What's 1 minus 1? You got 0. Then you are saying If it's one standard deviation away, it's like this, right? One standard deviation away, one standard deviation away. Then there will be at least 0% of data points in that range. I mean, that's not really useful. I mean, 0%, right? I mean, it's not really meaningful. That means you have something, right? Within one standard deviation away, right? It's not like this number that just useful. That's the reason we usually require k is bigger than 1. Okay. Let's use some example here to apply what we just learned. Okay, everybody? We have some example. Using example is always easier, is that right? Using example, okay? Otherwise, you may get confused what I'm trying to say here. Now, this example here is they are talking about, let me see, talking about in some neighborhood, okay? In some neighborhood, they have some example here. They are like the average house price. Someone was asking what is a K stands for, right? K stands for, right? That means how many standard deviation away from the center, from the average. So in our case here, if K is equal to 2, that means 2 standard deviation away, right? So in that case, we cover the 2 standard deviation away. 2 standard deviation is 1, 2, right? And also going down, right? 1, 2. So those are 2 standard deviation away. So K is the meaning, how many standard deviation away. Okay. K is not the standard deviation, okay? It's like how many standard deviation, away, okay? Let's use some example here. You understand it better, everybody. In case if you have questions, let's follow this example here. So you know what I'm talking about. So in some neighborhood, they are given the average price. It's like for example, this one here, right? Okay, it's about 50K. Let me draw that. Say here is about 50K in some neighborhood. Okay, standard deviation is about 10K, right? So you will see like some data points, sometimes high, right? Like that. Okay, trying to draw some data points here. Okay, trying to draw that. Okay, average we know that 50K. Okay, 50K. Now, standard deviation, like based on this neighborhood, we calculate the standard deviation is about 10K, right? Now we want to find out. We want to find out what's the price range so that at least 75% of values, right? They will fall in that range. So what does that mean? That means we want to find out like some range here, some range here, right? Try to see what is the, say in this range. So we know like at least 75% of data points, right? 75% of the house, right? They will fall in this range. Okay, so the question here is, how do we find out this range? Like what's the maximum here, right? What's the minimum here? Everybody? Okay, so how do we solve this? This 75%, everybody, that's the tricky part I want you to remember. In the beginning, I say, I'm not going to ask you too many case, right? 75%, if you remember previously, whenever we have 75%, corresponding K should be equal to what?
2.
You see, that's right. So 75% always, it is about 2 standard deviation away, right? Earlier, I say, how about like 3, right? So say on the exam, on the homework question, I change this question. Instead of 75%, I'm asking, how about 88.9%, right? So I'm asking, help me find out the range so that this range will cover 88.9% of data points. So in that case, I'm asking K is equal to 3. Okay, so those are the kind of stuff that it's like kind of tricky to tell you what is the K should be, right? Now, with this information, now we know is what K is equal to 2. So that means what? 2 standard deviation away. So that means, like, say now we're starting from the middle, everybody, 50K. We are going above by 2 standard deviation away, right? So 1, 2, for example, right? So 1 standard deviation is what? 10K.
10,000.
Yeah, 10,000. So we are 50,000 plus 10,000. We got 60,000 in the 1 standard deviation above. And then 2 standard deviation is what?
70,000.
That's right. That's the upper range. Similarly, for the lower range, right? 50K minus 10, we got 40. And continue to minus another 10K, we got 30. So the range would be, the answer should be what? Should it be between 30,000 to 70,000. So that range here, we know that we will cover at least 75% of them. That is applied to any data sequence. Okay, could it be more than 75? Like 78, 76, 80, 90, any number bigger than 75 is okay. Okay, so that's the Chebyshev theorem tells us. Everybody, that's the application I want to remind you here. Whenever you see 75%, remind you how many standard deviation away? 2 standard deviation away. Okay, now if I change the question, say 88.9% away, then remind you K should be equal to 3. Okay, and I said one more case here. You can do the calculation by yourself. K equal to 2.5. What's that corresponding to? You can find out by yourself. Okay. So that's for the Chebyshev theorem. One more thing I want to mention that here is there are certain situations the distribution could be even better. What does that mean? That means is Chebyshev theorem tells us if it's 2 standard deviation away, at least 75%, right? But if you have some data distributed like this, what do we call this bell-shaped form, right? It's more centralized, right? You will see more data points in the middle, right? Those we call, later on, we will spend more time to study this. We call this normal distribution, right? Or you call this bell distribution, right? For those ones, they are more centralized. So if it's 2 standard deviation away, everybody, if it's 2 standard deviation away, that means like 1 standard deviation away, 2 standard deviation like that. 1 standard deviation away, 2 standard deviation away, like this range here, like that. They should cover like 85% of data points instead of 75. You see, 75 applies to any data sequence, okay? But for some really like more centralized distributed data set, could be higher, right? If it's a 3 standard deviation away, everybody, if you remember the calculation we did earlier, that should be corresponding to at least 88.9%. For this normal distribution, right, we have even more centralized distribution here, 99.7%. Everybody, this part here, you don't have to remember this part here, okay? Let me highlight that. So what I'm talking about is this part here. Now, if you get confused, like how do we get a 95? How do we get a 99.7? Right? How do we get a 68? No worries, okay? Later on, we will spend more time trying to study this section, okay? So right now, I do require you to understand like the previous example case, okay? Like they help me find out what's the range, right? Like those ones, we do require those. Make sure you understand how to apply those one we just learned. Okay, so that's for the application for this Chebyshev theorem.